Hi guys, what I'm going to have here is the first part of the gas lecture, which is chapter 5 in the textbook. And I think this is going to end up being probably 4 different videos. This one will be the first one that we encounter. So let's go ahead and start taking notes on gases, chapter 5. So the first thing I'd like to put on the board about gases is that gases are the simplest and most well understood state of matter. So as we know, there are 3 states of matter: solid, liquid, and gas. There's a reason that gases are encountered so early in Chem 101 and chapter 5 because they're the simplest to understand and they're the most well understood state of matter. And the reason that they're very well understood is that they obey very simple to understand laws. So remember, nature has its own laws that it obeys, and the laws that gases obey, which we call the gas laws, are very simple in terms of their relationships, their algebraic equations. And what we're going to do is learn several of those laws in this chapter. So the solids and liquids are much more complicated, and you learn about those later in the textbook, chapter 11, I believe, but probably not encountered too much in Chem 101. So moving on to kind of introduce the topic of gases, I think it's important to just lay this foundation right at the beginning. The key point here is that there are 4 measurable properties of any gas sample. And to learn, it's important to learn these 4 properties first, lay out what letters we use to describe each of these 4 properties, and then these are the letters that we're going to be using in all of our equations. So let's go ahead and just, for the sake of thinking about it here, get a gas sample. I'll just draw it in a little container. Let me go ahead and put a top on the container. A gas sample is going to need a top or a cover, because if you have gases in a sample, if you don't put a top on it, they're all just going to escape into the surrounding area. So you always just have a top on your container when you're thinking about gases, so you can have an enclosed system. And let me go ahead and just pick any gas. For the sake of this lecture, I'll just pick CO2, which, as you know, is carbon dioxide gas. It's the gas that we are breathing out. And so when we think about a gas sample, the CO2 is what you would call the identity of the gas, the type of gas. This is not a measurable property. It's just the identity of the gas. So it could have been CO2, it could have been ammonia, NH3, it could have been O2, it could have been a bunch of different gases, methane, CH4. I picked CO2, but that's not a measurable property. That's just the identity. So the 4 things that I'm listing here are 4 things that you can measure about this gas sample beyond like what type of gas it is. And in no particular order, let's go ahead and list the properties. The first we're going to talk about is pressure. We can measure the pressure of a gas. Pressure, we're going to use a capital P in our equations. And I'm going to talk more about what that is in just a moment. The second thing in no particular order is the temperature. You can measure the temperature of a gas. And that is capital T, because lowercase t in chemistry is time. So capital T for temperature. The one thing I'd have you add in your notes right away is that if it has to do with gases, and if you're using any of these gas laws that we encounter in this chapter, all of your temperatures must be in Kelvin. And we will review how to convert from Celsius to Kelvin when the time comes. But for now, if you keep your temperatures in Celsius, you will get the wrong answers for all of your equations. All of them have to be in Kelvin if it has anything to do with gases or gas laws. The third thing that you can measure about any gas sample is the volume of a gas, and that would be capital V. Lowercase v, we will learn later when we learn kinetic molecular theory, is velocity. So capital V is volume. And once again, that's just the amount of space that something occupies. Keeping in mind that the volume of a gas sample is simply the volume of the container. So sometimes in a question, it might say CO2 gas in a 3-liter container, but what you have to understand is that that is not just the volume of the container, it is the volume of the gas itself, because the gas is going to fill up the whole container. So that's just one thing to keep an eye out, like when you're solving your problems. And then the fourth measurable property that you can get numbers for of any gas sample is the number of moles. And number of moles is literally just counting the number of particles in the gas sample. That's something that you can measure. Of course, we don't count molecules, individually, because that would take too long. There's always bazillions of them. So we count them by moles, chunks, which once again is counting by 6.022 times 10 to the 23rd. If you have 1 mole, that's how many particles you have. If you have half a mole, you have 3.011 times 10 to the 23rd. So that's the idea there. And the letter that we use to talk about number of moles is a lowercase n. Now these are the variables, the letters that you use in your equations. Obviously the units that follow the number are different. The units for moles is mole. The unit for volume is almost always liters. The unit for temperature, like I said, is Kelvin. And the unit for pressure, what we're going to find out and talk about in just a minute, is going to be atmospheres for us. But there are other pressure units as well. So we'll talk about that in just a second. So these are our 4 things that you can measure about any gas sample. The most new one, I suppose you could say, is pressure. So we're going to take some time and talk about pressure. What is pressure? How does it come about? And what are the units? So let's just go ahead and talk about pressure. What is pressure? So first, an answer to the question in the form of a sentence. So pressure is the force exerted per unit area by gas particles as they collide with the surfaces, or I'll just say surface of the container. So pressure is the force exerted per unit area by gas particles as they collide with the surface of the container. And the key word I've underlined here is collide. Pressure is all about the collisions with the surface of the container. So let's go ahead and draw a drawing. This will help us understand. Probably the most common thing that we can think about with pressure is like a tire, because most people have some sense of tire pressure. So this is my attempt at a tire. Let me go ahead and draw some gas particles in the tire, which would just be air, and I don't even know exactly if there's specific type of air, gases that they put in, but it really doesn't matter. Let's just go ahead and draw some gas particles. So one thing right off the bat, you see what I've drawn is that a gas sample, and there's a lot here, even in this little simple drawing. A gas sample is mostly empty space. And that's because the particles in any gas sample, no matter what type of gas it is, particles are very far apart from each other. So when you picture a gas, it's important to picture it right. And that's how you want to picture it. It's mostly empty space with the particles really far apart from each other. In addition, the particles are not just standing still. The particles are in constant motion. So let's go ahead and draw a couple things to indicate that. So sometimes they're moving in just random directions. So the particles are also in constant motion. Let me write that on the board. Constantly moving. Just picture like ping pong balls just flying all over the place in all different trajectories. So in this drawing here, I've drawn these two just hitting each other, and that will happen. And they'll hit each other, but that doesn't create pressure. What creates pressure is the random collisions with the sides of the container. So for instance here, if you have the gas particle hitting the side of the container, this force creates pressure. It's the force on the side of the container. Or I should say the collision with the side of the container. Hold on one sec. Okay, I came back. Okay, so, you know, this one would create pressure. This one would create pressure. This collision with the side of the container would create pressure, and so on. So it's the collisions with the side of the container that are going to create pressure. Now, if I think about tire pressure for a minute, if my tires are low in pressure, what do? You add air. So you add air to your tires when they're low in pressure. So let me just use red to indicate the added air. So when you add air, you add more particles, and more particles in your tire would mean more collisions, and that's exactly how you would increase your tire pressure. That would get it up to whatever it needs to be to drive efficiently or whatever. So that's the concept. If you have more collisions, you have more pressure, just because you have more particles. So that's the sentence description of what pressure is. It's all about getting more collisions with the sides of the container. But the other way of thinking about pressure is an equation. So mathematically, pressure is equal to force per, you see the word per, which in math is essentially a fraction line, force per unit area. So this is another way of thinking about pressure, which is just more of a mathematical approach to it. But it's essentially the same as this sentence up here. It's the force per unit area by the collisions. Anytime you get a collision, you exert force. If I throw a ball at the wall, it's going to exert a force on the wall. Okay, let's now talk about the units of pressure. And we'll talk about this area aspect in a minute. Actually, you know what? Let me just address this real quick here. Well, maybe I won't go too far into that, but it's basically, it's not just the total amount of forces, but it's how they're spread across the area of the surface. So if you have less area that the collisions are colliding with, that actually is going to increase your pressure because you're not spreading out the collisions over as great a space. So anyways, that's where that comes into play. So that affects your pressure as well, how your forces are, or your collisions are spread out. All right, anyhow, so here's the units of pressure. So let's talk about the SI unit. The SI unit for pressure is the Pascal, which is named after Blaise Pascal, a scientist. So this is the formal SI unit, and it's capital P, lowercase a. I do want you to know that a Pascal, so 1 Pascal, is equal to 1 Newton per square meter. 1 Newton per square meter. A Pascal is actually considered a derived unit because it's derived from smaller units. So let's talk about this for a minute here. What in the world is a Newton? A Newton is the SI unit for force. A Newton is the SI unit for force, is International System Unit for force. And area, the SI unit for area is a meter squared, which makes sense because think about the simplest shape here, like a square, that you could take the area. The area is not a 3D thing, it's a 2D thing. So area is length times width. And each of these would be measured in meters according to the SI system. So if area is length times width, your unit ends up being meters squared. So that's why the SI unit for area is meters squared. And that's why the SI unit for pressure is the Pascal, because it's essentially just derived by putting these two things together. The other kind of famous unit for pressure that we use with tires is the PSI. And PSI stands for pounds per square inch, which is the same concept here. Pounds is another unit for force, not the SI unit, but it's another way that we measure force in science, kind of like the more American unit, pounds per square inch, which is just another American way of, if you would measure these in inches, square inch is just another area unit for area. So that's just another unit for pressure. Neither of these are going to be used in our class though. So even though I want you to be familiar that they are pressure units, we are not going to be using them. The unit that we are going to use almost exclusively in this chapter is the atmosphere. The atmosphere is abbreviated ATM. So be familiar with that. The atmosphere is another unit for pressure. In addition, another unit for pressure that I want you to know is the torr, T-O-R-R. These are just different ways that scientists can measure pressure. The torr has a, I guess you could say a synonym, and that's the millimeter of mercury. So a torr is a millimeter of mercury. This is another pressure unit. Kind of like 1 milliliter is equal to a cubic centimeter, like you can interchange the two. The same is true for the torr and the millimeter of mercury. So these 1, 2, 3, 4, 5 units, I want you to be familiar with it. These are pressure units. I want you to also recognize that that the Newton is a unit of force, not of pressure. Okay, so staying on that just a hair longer about the units, there's 2 things I want you to know beyond this here, but in relationship to the units for pressure. I am not going to be asking you to convert between units of pressure. It's just something we're not going to require you to do. However, for a homework problem, at least one of them, you are going to have to convert between torr and atmosphere. So you are going to have to be familiar with this conversion factor. Just understand that it's a conversion factor just like any other conversion factor. You just use it. In atmosphere, 1 atmosphere is equal to, these are the same amount of pressure, 760 torr. So for instance, if you're given something in torr, just use this conversion factor to convert it to atmosphere. So I think everybody's pretty familiar with how to use conversion factors. And then the last thing I need to say about the about pressure units is that the atmospheric pressure, and I'll talk about what that is in just a second, at sea level is assumed to be 1 atmosphere. I'm writing 1.00 just to give us some sig figs, but 1.00 atmosphere. So sea level meaning we're not in Denver, we're in Maryland, someplace at sea level. So we're not talking about up in the mountains, but sea level. And what is atmospheric pressure? Atmospheric pressure is just simply the pressure of the air in the atmosphere. So for instance, I'm standing in a room, this is me, okay? And because of the fact that there's air all around me, there's gases all around me, there's gases all around you. And what are they doing? They are hitting me. I'm essentially, they're part of their container. I mean, they're hitting everything else as well in the room, but they're also hitting me. And the pressure that I am feeling as part of this gaseous container is 1 atmosphere at sea level. So sometimes you'll have a question where it talks about the atmospheric pressure at sea level. You're supposed to kind of know that that's 1 atmosphere, kind of by heart. So, all right, so we've got the units for pressure. We have what pressure is, which is just the forces exerted per unit area on the sides of the container. We have that pressure increases the more molecules you have, the more collisions you have, the more pressure you're going to have. And that is good enough for this part here. Now, moving on to the next part of this lecture is it's time to start learning about the gas laws. And what we're going to start with are the 3 simple gas laws. The 3 simple gas laws. There's actually a 4th, but I'm just going to teach you the 3 that are highlighted in the book. Boyles, Charles, and Avogadro's. And let's start out by just kind of making something a little bit clear here. A lot of times people see simple and they would think easy, or easy to understand or something like that. In this context, that's not really what simple means. So let me kind of go ahead and, it's not that they're hard, they actually are kind of easy, but let's talk about what it means to be a simple gas law. What is the word simple talking about here? So all 3 of these laws, describe the relationship between 2 gas properties while holding the other two constant. And that's what it means to be simple. Remember, we talked about there's 4 gas properties, P, V, hold on one sec. Yep, P, V, T, and N. So 4 gas properties. All the simple gas laws will describe how one of those affects another one of those, but in the context that the other 2 are not allowed to change. They have to stay constant. And that's really how a lot of science is done. You can't, you need to control, certain properties of a system or whatever to look at how one thing affects the other thing. So that's exactly what these are going to look at, are going to examine. And that's why they're called simple. It's kind of like reduced in a way, like focused on just 2 properties at a time. All right, so in no particular order, this is just the order that the book covers them. In fact, you know what I'm going to do? I'm going to erase my board so I have more room. But the first one that we're going to talk about is Boyle's Law. And they're all named after the scientists that discovered them. And once again, these are not inventions, these are discoveries. Laws are just describing how nature behaves. And these are things that are just discoveries by careful experiments, repeated experiments. And so Boyle discovered this very first law, and it was named after him. So let's go ahead, and all of these are going to be presented in the same fashion. So Boyle's Law describes the relationship between pressure and volume. All of them will involve, at least all of the ones that we're going to talk about, involve volume in one way, shape, or form. So this one is looking at volume compared to pressure. And what is assumed is that you are holding the other 2 properties, which, as you remember, are temperature and number of moles constant. So Boyle's Law is always assuming that you're holding these 2 constant. You're not allowing them to change. Keeping the temperature the same, different ways to do it. I mean, if there's no chemical reaction, whatever, you would just keep the environment the same. Do it in room temperature or keep it in a cold temperatures or whatever. Holding the number of moles constant is as simple as this. If you have a gas sample, as long as you have a lid on the container, and there's no chemical reactions happening or anything, you're just having a gas sample, as long as the lid is on, no gases can escape and no gases can come in, so your number of moles will stay constant. It's as simple as that. Put a lid on the container. That will keep your number of moles constant. All right, so what did Mr. Boyle discover? So first, let me go ahead and present it to you this way. Let me present it to you as the proportionality. So what Boyle discovered was this proportionality. This is something kind of new. So go ahead and just jot this down. Volume, and then this little sign, kind of like an at sign, 1 over P. So in math, that little sign right there is how we describe is proportional to. Proportional to. So with proportionalities, we're looking at relationships. Is proportional to. Okay, so when you see a proportionality that's presented like this, volume is proportional to 1 over P. What that means, and I'll first give you the conclusion and then I'll describe it here, is that as pressure increases, volume will decrease. And as pressure decreases, volume will increase. And so let me explain that part here. So first of all, let me go ahead and describe this here. When this type of proportionality, when one thing goes up, the other thing responds by going down. You can say it the same way here. When one thing goes up, the other thing responds by going down. This is what we call an inverse proportion. When one goes up, one goes down, because we're going to learn two types of proportion. Inversely proportional, let me say it like that. We're going to learn the other type as well, which is going to be directly proportional. But this is an inversely proportional relationship. When one goes up, the other one is going to go down. And think about that. It actually does make sense. If I put in just here the number 2 for P, volume is going to be 1/2. But if I make that number bigger, let me make it a 10, volume becomes 1/10. So as I made pressure a bigger and bigger number, my volume went from 1/2 to 1/10. And 1/2 is 0.5, 1/10 is 0.1. So you'll see that volume actually went down. So when you put in larger and larger numbers into a denominator, the other number over here would naturally get smaller. So bigger and bigger becomes smaller and smaller. And that's exactly why the proportionality is written in this form, where the pressure is in the denominator. At the end of the day, mostly I want you to know this. These volume and pressure, which is what Boyle discovered, are inversely proportional. When one goes up, the other one has to go down. So that's the first part, is that these two are inversely proportional. We are going to come back to this guy in just a minute, so I might leave him up for a second. But let's go ahead and explain the why. Why is that? All of these are actually very easy to understand. When it comes to pressure and volume changes in this type of context here, it's actually very helpful to learn how to draw one of these little containers that has like a movable piston. So I've got a square. I'm going to actually just draw like a little picture a person's hand right here with like a plunge of being able to push this thing down here. So let me have a gas sample in here. You just draw 6 here. And remember, these are always moving. If they're gases, they're moving, they're hitting each other, they're hitting the sides of the container, they're creating pressure. So I've got my hand on the plunger. So just picture this, and you have a gas sample in here. Let me go ahead and decrease the volume by pushing down the plunger. It's just a very simple way of picturing a gas. So I've just basically pushed down that plunger. And sometimes the more you advance in chemistry, the more you will find these kind of diagrams really valuable to understanding things. So what I have done in this sample is I have decreased the volume of the sample. Boyle has discovered that if you decrease the volume, you are going to increase the pressure. We come at it already knowing that they're inversely proportional. Why is the pressure increased in this sample? Why? And the reason is, hopefully it actually comes back to this, what we talked about earlier, is that you still have the same number of particles. You have 6 particles over here, you have 6 particles over here. But there's 2 things going on. Number one, they actually don't have to travel as far to get to the sides of the container. So you're gonna collide with that container more often. But also, you have just decreased the area over which you're spreading these collisions. So here you had all of this area to kind of accept those collisions. Whereas here now your area where those collisions are happening is decreased. And for the very same reason here, if you put smaller and smaller numbers in here, so in a denominator, if your numbers keep going smaller and smaller, so say you go from, fake numbers can help here. If you go from 1/20 to 1/3, if you put smaller numbers in a denominator, you end up increasing the result. 1/3 is much bigger than 1/20. So that's the concept here. Smaller area over which to spread out your collisions, you're going to get more pressure. So that's the concept of Boyle's Law. That's the reason pressure increases when volume decreases. So that's the why. All right, so the next thing about Boyle's Law, and Boyle's Law is going to take the longest just because we have to lay out a few kind of ground rules or whatever. The other laws will be faster to talk about. So you know the proportionality, inversely proportional. We know the reason why. Now, what we want to do is we want to figure out the equation for Boyle's Law. And then we'll show you an example of how to use it. So coming back to the proportionality, a proportionality is not an equation. The equation must have an equal sign. Equal says equation. And this is not an equal sign. This just describes relationships, but it's not going to allow us to do calculations. At the end of the day, we need equations so we can calculate numbers. The whole concept of a calculator is with an equal sign at the end of it. So you need equal signs. So in chemistry, in math, if you want to replace a proportionality sign with an equal sign, you are allowed to do it. And so I'm going to have you guys kind of learn how to kind of do these types of mathematical conversions. I think it's really helpful. You're allowed to create or to replace it with an equal sign, but only under the pretext that you insert what's called a constant right after that equal sign. And so I'm literally just doing what math requires, which is I can replace it with an equal sign as long as you put a constant right there. Let me go ahead and just turn this into something a little bit more friendly. V equals constant over P. All I did was times the constant by the number 1. All right, so far so good. We're just doing what math requires. We're turning it into an equal sign. Now let me do another mathematical rearrangement. Let me times both sides by P. And then you will see that PV has to equal a constant. All right, and here we're getting closer to the equation that's famous for Boyle's Law. And you're not going to have to do this on the exam. I just want you to understand where the equation comes from, that it's just really a reflection of the proportionality. All right, so in that little example where I had that little plunger 2 seconds ago, where I had it from here and then I pushed it down, remember? Okay, in both of these, the before and the after situation, both of these PV had to equal a constant. So let me go ahead and describe this one, P1 and times V1. In other words, the before I'm going to use ones to indicate which pressure and which volume. And the after I'm going to use twos. So this is P2 times V2. The concept here is this. If both of these have to equal a constant, which is a number that can't change, I didn't say that, but a constant is a number that can't change. If this one has to equal the constant, which it does, and then I push down the plunger and this one has to equal the constant. The idea here is this: if they both have to equal the same number, then they equal each other, just by logic. And what we've just discovered is the equation form of Boyle's Law. P1V1 equals P2V2. And in fact, this is probably the most famous form of Boyle's Law. P1V1 equals P2V2. So anytime you have a sample, if you change the pressure or the volume, the P1V1 before has to equal the P1V1 after. All right? Or the P2V2 after. Let me go ahead and put a practice question up, and then that will end up, and then I want to show you one quick graph, and then we'll end up concluding this video. So, practice question. All right, a sample of, let's pick of neon gas. A sample of neon gas has an initial volume of 13.9 liters at 1.22 atmospheres. If you compress the sample, and understanding when you compress the sample, what you are doing is you are essentially pushing down that plunger. You are lessening the volume. So if you compress the sample to 10.3 liters, you can see that I did. I went from 13.9 liters and I made it 10.3 liters. The question is, what will its pressure be? And these questions are all about just reading it carefully and picking out what each number represents. So, sample of neon gas. First of all, something about this I want you to notice. It doesn't matter the type of gas. There's nothing about molar mass or anything like that. P1V1 equals P2V2. I could have written CO2. I could have written CH4. It doesn't matter the type of gas. I put that in there just so that you can understand that that's kind of often come as part of the problem, but you're supposed to understand it doesn't matter the type of gas. It has an initial volume of this. Hopefully you can see initially it was 13.9 liters. Liters is a volume unit. That's your first volume, initial volume. And this is your initial pressure, 1.22 atmospheres. That's what it was before you've changed it. And now you go ahead and change it. You compress the sample. You do something to your sample. And what would this number be? Hopefully you can see that that is your second volume, your after volume. And what are you solving for? You are solving for the new pressure. So understanding it's like a before and after. You had it one way, then you changed it. Now on an exam, I wouldn't tell you to use Boyle's Law. You would have to recall this law by heart, and you would have to just see that based on what's been given and what you're being asked, that these are the types of variables that show up in Boyle's Law. And then it's just a matter of solving. One nice way to do this is to first write the law down that you're using. P1V1 equals P2V2. And immediately, even before you start plugging numbers in, solve for or rearrange for who you're solving for. So you need P2. So I need to make P2 by himself or isolate him. V2 is in the way, and I can get rid of that by dividing both sides by V2. Therefore, P2 is going to equal P1, which is the 1.22 atmospheres. Be very diligent about making sure you write your units in there. You're going to want to see them canceling or surviving. It's an important part of these gas law problems. You'll see as we do more how important it is. But don't ever drop your units. That number is not 1.22. It's a measurement with a unit, so you write the whole thing. P2 equals P1 times V1, which was 13.9 liters, over final volume, or V2, which is 10.3 liters. You can see the liter unit will cancel nicely, and you're going to be left with atmospheres, which is perfect. So go ahead and throw that into your calculator. And I am getting an answer of 1.6464, but let's check out the sig figs. I've got 3 in all of these, so I'm just going to pick 3 sig figs, 1.65. And the unit that survives the canceling is atmospheres, which makes perfect sense because it is a pressure, and that would be the answer, 1.65 atmospheres. With all of the gas laws, it's really important, or I think helpful at least, to think about whether it makes sense. So step back at the very end and think to yourself, because it will allow you to catch errors sometimes. We have compressed the sample. Volume has gone down. Boyle's Law states that pressure will have to go up. And then step back and see if it did go up. Well, it used to be 1.22, now it's 1.65, perfect. So that's a way to check, because if you saw it going down, that would be impossible. So probably means you did something wrong with your numbers. Plugged it in wrong to your calculator, did the algebra wrong, or whatever. Okay, that is a classic Boyle's Law question. The last thing about Boyle's Law is, what does the data look like if you graph it? So for all of these, I also want you to know what a graph would look like of data. Like when Mr. Boyle was doing his measurements, his experiments, what did his data look like? For all of these, and it can be very, very rough. It doesn't have to be, you're not writing much here. For all of these, the volume measurement is on your y-axis. That's just a helpful thing to remember. And your whatever else you are examining is going to be on your x-axis. So for Boyle, he's looking at P and V, so that means pressure would be down here. You don't need any units, okay, to get kind of what I'm trying to get you to understand here. When Boyle did his experiments, he would get something that looked like this. This type of shape. So these are basically a bunch of different experiments, and you can connect them together if you'd like to get a line. But the shape of that curve would look like what I've drawn here. And just kind of just draw that into your notes, and then step back and make sure you understand this for a minute here. Look at what is happening to the, let's start here. Let's start example number 1, or experiment number 1. As Mr. Boyle is increasing the pressure, so as you're moving this way on your x-axis, because he's increasing the pressure every single time he does one of these experiments. What is happening to the volume? It's going down. You see that? And that is essentially what he discovered. As pressure increases, volume decreases. And you could say it the other way too. As volume decreases, pressure increases. As volume increases, pressure decreases. As long as you get that one goes up, one goes down, you're always saying the same thing. All right, so that is the last thing about Boyle's Law that you need to know. The next video will cover Charles' Law, Avogadro's Law, then we're going to get into the ideal gas law and some other things, STP, molar volume and density, I believe. So hang tight for the next video, but that's what I wanted to cover in this video. Good luck.